Now, in this session, we're going to cover rational and irrational numbers. The rational numbers are numbers in the form of p over q, where p and q are integers. Irrational numbers have been known to exist. They are numbers that you cannot represent adequately with just an integer, with a rational representation such as p over q. For example, historically, people have known for a long time that the square root of 2 is not a rational number. The proof of that is fairly simple. What you do is you pretend that it's a rational number, and then you square it and prove that when something is even and something else is also even, and that's just not possible, and so on. But that you have likely have already seen that proof at some point in your life, and we're not going to go over that. Now, what we are interested in is showing that between any two real numbers, no matter how close they are, there are always rational and irrational numbers in between them. The point of that is to mean that you can approximate any real number with rational numbers, and irrational if you want, but a real number with rational numbers. In other words, rational numbers are good enough to represent to approximate the entire real number system. There isn't a number that's out by itself away from rational numbers. Rational numbers are everywhere to be as close as you want. So here's what we're proving right now to show that if A is less than B, and A and B are real numbers, okay, they're all real. So then there exist M and N integers such that A and B is M over N is between A and B. So you can, in other words, if you imagine A and B to be really, really close, there's always some rational number standing in between them. Okay, no matter how close they are, they will never get to the point that there's no rationals left. They're always there. So how do you prove that? Well, there are many ways, but we're going to do it in our recent way, which is using the theorems that we've learned just recently. Okay, so first we go by, so here's the proof. First we go by the argument 1 is bigger than 0, and b minus a is bigger than 0, because we want to use the theorem that states if you have two positive numbers, then there exists a positive integer n, so that n multiplied by one number is going to be bigger than the other number. Okay, so now we have two positive numbers, so we will select n. So there exists n such that n times b minus a is going to be bigger than 1. All right, that's the first condition. And the second condition is we will choose the smallest, okay, this matters, smallest m, smallest is very important, smallest m, such that this condition exists. M is bigger than NA. Now, how would you choose the smallest m like that when NA is not necessarily positive? Well, we have recently proved something that says if you have a bunch of positive integers, then well, we know such m's exist first. Okay, we know we can pick an m that's eventually bigger than NA. But the question is, can we choose the smallest m? Well, recently we've read a theorem that says if you have a class of positive integers, then there's a smallest integer, smallest member in this class. Now that statement actually doesn't just apply to positive integers. It's any collection of integers that has a lower bound. That is, all the integers are bigger than a certain value. It doesn't have to be 0. The proof will work the same way. Then it has the smallest member. So, of course, intuitively, this is fairly easy to see that you can pick a smallest m such that m is bigger than NA, and m minus 1 is going to be smaller than or equal to NA. Okay, so m is close to n, n minus 1 right behind it. So then, and at this point, then now you start doing algebraic manipulations. with this sentence right here, this line right here. So what you have is then you rewrite this, you get m is less than equal to na plus 1. That's just rewriting this. And then which is and then you consider what is 1? 1 is less than this value, okay? So this whole thing is going to be less than na plus this value right here, this whole thing, n times b minus a. And this whole thing just equals to nb by the time you work through it. So if it's just equal to nb, then you have your conclusion, because that means the conclusion then becomes m is less than nb. Now notice the inequality, the equal sign is gone because the strict inequality kicked in right here. So m is less than nb, and then remember m is also bigger than na right here. Okay, m is bigger than na, which we will rewrite it here, bigger than na from this place. So then you just do the division, you got your inequality. M over n is between a and b. So that is your that is the proof. Now the next question is, okay, so there exists a rational number in between any two real numbers. What about irrational? How do we show that there's an irrational number in between two numbers? What you do is you pick some irrational number, such as the most famous one is the square root of 2. Okay. Now suppose you're giving two real numbers. You find the irrational number between them, which we don't normally care, but we'll do it anyway. So what you do is you pick square root of 2 or anything else that's irrational. So we pick square root of 2 and we consider this thing, square root of 2, a over square root of 2, and b over square root of 2. This is a real number and so is this. And which by what we just proved, there exists a rational number m over n that's in between them. Okay? So then you rewrite this thing, then you have what happens then is if you multiply square root of 2 across the board, then a will be between m square root of 2 over n and b. And this number right here will be the irrational number that you're looking for. The reason you know that it's irrational is because if it were rational, then very soon you can multiply it by n, divide by n, and prove that square root of 2 is rational too, which is a contradiction. So this is definitely an irrational number that you're looking for. So that's just a quick trick. Once you get to the rational, the irrational comes out pretty readily.